There is a planet spinning right now in the darkness between stars. It has no name. It has never had a name. No creature has ever stood on its surface and looked up. No mind has ever felt the weight of its sky pressing down on a chest full of questions. No eye has ever caught the light of its moons, and felt in that moment the particular human ache of beauty mixed with longing. It is simply there, spinning, as it has been spinning for 3 billion years, as it will keep spinning for 3 billion more. Its mountains are taller than anything on Earth. Ranges of frozen silicate stretching 40 kilometers into a sky that no atmosphere has ever touched. Its plains are cracked and ancient, scarred by impacts from the early chaos of its solar system's formation. Its core is cooling, slowly, the way all things cool when there is nothing left to sustain the heat, and it will die the way it lived, alone, unwitnessed, unremembered. Now multiply that planet by 1 trillion, by 10 trillion, by a number so large that every mathematical language human beings have developed begins to stutter and fail, because that is what the universe actually contains. Not dozens of empty worlds, not hundreds, not millions, trillions upon trillions of planets, moons, asteroids, dwarf worlds. All of them dark, all of them silent, all of them drifting through the cold in a state of profound and unbroken solitude. And somewhere in the middle of all that silence, on one small, warm, geologically restless rock, orbiting an ordinary star in the outer arm of an unremarkable galaxy, a creature evolved that could look up at all of it and ask a question. The question is not, are we alone? That is the question on magazine covers. That is the question that fills documentary series and late-night debates and the search programs of well-funded space agencies. The real question, the one underneath that question, the one that once you see it clearly you cannot stop seeing, is this: why did something build all of this and leave almost none of it inhabited? If there is a God, a creator, an intelligence, a will behind the structure of physical law, why would that will construct the most elaborate, most precisely engineered, most staggeringly vast machine in the history of existence, and then place life in such a microscopic corner of it that the margin of error in our cosmic measurements is larger than all of life's known domain? If there is no God, if the universe is the product of pure physics, of quantum fluctuations and mathematical necessity, then why are those laws so precisely calibrated that almost any variation produces a universe without atoms, without stars, without chemistry, without the possibility of anything complex at all? Either way, the emptiness demands an explanation. Either way, the silence is a signal. And today, we are going to follow it all the way down. Before we ask the philosophical questions, we need to sit with the numbers, not skim them, not let them wash over us the way large numbers usually do, triggering a brief sense of awe before the mind quietly moves on to something more manageable. We need to actually sit with them. The observable universe, the portion of space from which light has had time to reach us since the Big Bang, stretches approximately 46 billion light-years in every direction. A light-year is the distance light travels in 1 year, moving at approximately 300,000 kilometers per second. To cross a single light-year in a spacecraft traveling at the speed of a commercial aircraft would take approximately 11 million years. The observable universe is 93 billion light-years across. These numbers are not meant to impress. They are meant to establish the scale of the problem we are dealing with. Inside that 93 billion light-year sphere, there are an estimated 2 trillion galaxies. The word trillion has become so common in economic discussions that it has lost its ability to land with appropriate force. So let us be precise, a trillion is a million millions. If you spent $1 per second, it would take you 32,000 years to spend $1 trillion. The universe contains 2 million of those amounts of galaxies. Each of those galaxies contains, on average, somewhere between 100 billion and 1 trillion stars. Our own galaxy, the Milky Way, contains between 100 and 400 billion stars. It is not a large galaxy. It is not a small one. It is average, unremarkable, one of 2 trillion. Around those stars orbit planets. Current estimates, based on data from missions like the Kepler Space Telescope, suggest that on average, every star in the galaxy hosts at least one planet. Many host more. This gives us, for the observable universe alone, a conservative estimate of something in the range of 10 to the power of 24 planets. Written out, that number looks like this: 1 million, million, million. A 1 followed by 24 zeros. If you began counting those planets at birth and counted 1 per second for your entire life, you would not reach 1/trillionth of the total. Now, of all those planets, all those incomprehensible trillions of worlds, how many have we confirmed host life? 1. This one Earth. 1 confirmed example of life, in 10 to the power of 24 possible locations. That ratio, 1 in a trillion, is not just a scientific curiosity. It is one of the most profound facts in the history of human knowledge, and yet it receives a fraction of the attention it deserves, because its implications are so uncomfortable that most conversations quietly steer around them. Let us not steer around them. Every complex system was built to do something. A bridge exists to allow crossing. A heart exists to pump blood. A telescope exists to extend the range of human vision. When we evaluate a system, when we ask whether it is well designed, we ask whether it accomplishes its purpose efficiently. We look at the ratio of resources invested to output produced. Now apply that framework to the universe. If the universe's purpose is to produce life, to generate consciousness, awareness, the capacity for experience and understanding, then by any engineering standard, it is performing catastrophically. 13.8 billion years of operation, an investment of all the matter and energy that exists, a rule set, the laws of physics, of extraordinary elegance and precision, and the output, as far as we can verify, is life on one planet. If a company released this product, with this ratio of resources to output, every investor would demand an explanation. The universe, by this measure, is either the worst designed system in existence, or it is extraordinarily good at something we have completely misidentified. Or, and this is the possibility that quietly unsettles physicists at conferences, life is not the product at all. And we have been asking the wrong question from the beginning. Let us hold that thought and approach from another direction. Imagine you are not a physicist or a philosopher. You are an engineer. Practical. Focused on mechanisms. You have been handed the specification sheet for the universe and asked to explain why it produces so little of what it seems to be designed to produce. You begin with the chemistry. For life as we know it to exist, you need carbon. Carbon is the only element with the chemical flexibility to form the long, complex, stable molecular chains that biology requires. A universe without carbon is a universe without life. At least without any life resembling what we know. Carbon is not primordial. It was not present at the Big Bang. The early universe contained only hydrogen, helium, and trace amounts of lithium. Everything heavier, every element that makes chemistry interesting, had to be manufactured. The factory for heavy elements is a stellar core inside a star. Hydrogen fuses into helium. In larger stars, helium fuses into carbon. Carbon fuses into oxygen, neon, magnesium, silicon. In the most massive stars, the chain continues all the way to iron. This process takes time. Millions of years for the most massive stars. Billions for stars like our sun. And when those stars die, when they exhaust their fuel and collapse and explode, they scatter those heavy elements across space, seeding the gas clouds from which new stars and planets form. Second-generation stars. Third-generation stars. Each generation richer in heavy elements than the last. Our sun is a third-generation star. The Earth was formed from the debris of 2 previous stellar generations. The carbon in your body was forged in stars that died before the solar system existed. This is not a metaphor. This is documented, measurable, chemically verified history. And what it means for our question is this. There is a minimum amount of time a universe must be running before life becomes chemically possible. You cannot have life in the first generation of stars. The heavy elements do not yet exist. You cannot have life immediately after the second generation either. The elements exist, but the process of planet formation, geological stabilization, and chemical complexity requires additional billions of years. The pipeline from Big Bang to biology has a minimum length, and that length is measured in billions of years of mostly empty, mostly lifeless, mostly silent universe. The emptiness is not incidental. It is structural. On a summer day in 1950, the physicist Enrico Fermi was having lunch at the Los Alamos National Laboratory with colleagues. The conversation, as it often did among physicists at that time, had wandered to speculation. The topic was extraterrestrial intelligence. Someone had mentioned a recent New Yorker cartoon about flying saucers. The discussion meandered through probability and distance, and the age of the galaxy. And then Fermi, who had a gift for reducing complex problems to their essential absurdity, looked up from his food and asked a question that has haunted science ever since. But where is everybody? 4 words. And they changed the way physicists think about the universe. Here is the logical structure of what Fermi was pointing at. The Milky Way galaxy is approximately 13 billion years old. It contains, conservatively, 100 billion stars. Even if only a small fraction of those stars have planets, and only a small fraction of those planets develop life, and only a small fraction of those develop intelligence, the numbers still suggest that intelligent life should have arisen billions of years ago, long before Earth even formed. A civilization with a billion-year head start on us, even one advancing at a fraction of what we might consider a normal technological pace, should have had more than enough time to explore or colonize the entire galaxy. They should be everywhere, or at minimum, they should be impossible to miss. Their electromagnetic signatures, their engineering projects, their attempts at communication, all of it should be detectable by now. And yet, silence. Decades of searching. Multiple dedicated programs scanning the skies across every radio frequency. The SETI Institute alone has been listening continuously for over 60 years. More recently, the Breakthrough Listen initiative has scanned millions of stars across a range of frequencies with instruments of extraordinary sensitivity. The result is always the same. Nothing. No repeating signal that cannot be explained by natural phenomena. No mathematical pattern. No structured transmission. No artifact detected near any star. No megastructure. No Dyson sphere. No sign that anywhere in the portion of the galaxy we can observe, any mind other than ours has ever reached for the stars and tried to make contact. The silence is not a data gap. It is a data point. And it means one of several things, all of them profound. The first possibility, intelligent life is extraordinarily rare. Perhaps we are genuinely alone, or nearly so, in the galaxy. Perhaps the emergence of intelligence from biology is so improbable that in a galaxy of hundreds of billions of stars, it has happened only once, or only a handful of times. The second possibility. Intelligent life is common, but civilizations do not last. Something. War, environmental collapse, the development of technologies that cannot be safely managed, reliably ends technological civilizations before they can spread or make lasting contact. This is the great filter. And the terrifying version of this hypothesis is that the filter lies ahead of us, not behind. The third possibility. Civilizations exist but are not communicating in ways we can detect. Either they have moved beyond electromagnetic communication entirely, or they are deliberately silent, or the distances involved make contact practically impossible across the timescales of any individual civilization. The fourth possibility, and the one that reframes everything, is the one we touched earlier. The universe is not empty of intelligence, because intelligence is impossible. The universe is mostly empty of intelligence, because we exist at an extraordinarily early point in cosmic history. The universe is 13.8 billion years old. To a human being, that number is incomprehensible in the direction of largeness. We cannot viscerally feel the difference between 1,000,000 years and 1,000,000,000 years. Both feel like forever. But here is something astrophysics has recently revealed that reframes that number completely. 13.8 billion years is not old, not in the context of how long the universe will continue operating. Current models of stellar physics predict that the universe will produce stars for approximately 100 trillion years. 100 trillion. The current age of the universe, 13.8 billion years, represents approximately 1/10,000th of the total star-forming period. If the universe's star-forming lifetime were compressed into a single calendar year, we exist on January 1st, before noon. And the type of star that will dominate the universe's future is not the hot, bright, relatively short-lived stars like our sun. It is red dwarf stars, smaller, cooler, dimmer, and almost unimaginably long-lived. A red dwarf star with half the mass of our sun will burn steadily for approximately 50 to 100 billion years. The smallest red dwarfs will burn for trillions of years, longer than the current age of the universe by factors that strain comprehension. And red dwarf stars have planets, many of them, some in the right temperature range for liquid water, some with the right chemistry, the right geological activity, the right atmospheric conditions for the kind of slow, patient, accumulating complexity that produces biology. The astrophysicist David Kipping performed a careful analysis of when in the universe's history the probability of life peaks. His finding, not now. The peak comes far in the future, when the long-lived red dwarf stars have settled into stable, reliable burning and their planets have had sufficient time for complexity to develop. We are not just early in human history. We are early in the universe's biological history, which transforms the meaning of the Fermi paradox entirely. The silence we hear when we listen to the cosmos may not be the silence of absence. It may be the silence of earliness. The silence of a universe that has barely begun the phase in which intelligence becomes common. We may not be alone in the universe in some absolute sense. We may simply be among the first, and being first, truly or nearly first, in the history of an entire universe, is a different kind of solitude than simple loneliness. It is the solitude of the pioneer, the one who arrives before the others, the one who stands in an empty landscape that will eventually be full of everything, but not yet, not for a very long time. Let us talk about something that makes physicists genuinely uncomfortable. The universe runs on rules. We call them the laws of physics, or the fundamental constants of nature. They describe everything from how atoms hold together, to how galaxies form, to how light behaves across billions of light years of empty space. These constants have specific values. The gravitational constant, the speed of light, the mass of the electron, the strength of the electromagnetic force, the ratio of the strong nuclear force to the weak nuclear force. They are not derived from deeper principles. We cannot calculate them from first principles and show that they had to be what they are. We simply measure them and find that they have these values. And here is where it gets strange. When physicists ask what would happen if those constants were slightly different, not dramatically different, just slightly, fractionally different, the answer is almost always catastrophic for complexity. If the gravitational constant were slightly stronger, stars would burn through their fuel in millions of years rather than billions, leaving no time for complex chemistry to develop on orbiting planets. If it were slightly weaker, gas clouds would never collapse into stars at all. If the strong nuclear force were slightly stronger, hydrogen would fuse too readily and burn out before any chemistry could happen. Slightly weaker, an atomic nuclei would not hold together. If the cosmological constant, the energy density of empty space, were slightly larger, the universe would have expanded so rapidly after the Big Bang that no structure would ever have formed. Galaxies, stars, planets, none of it. Just a thin, cooling, endlessly expanding gas. The physicist Leonard Susskind has estimated that the cosmological constant is tuned to within 1 part in 10 to the power of 120 to permit the existence of a universe with structure. 1 part in 10 to the power of 120. That is a precision so extraordinary that it makes the human mind want to sit down quietly and reconsider everything it thought it knew about coincidence. The physicist Fred Hoyle, a committed atheist for most of his life, spent years working on stellar nucleosynthesis, the process by which stars forge heavy elements. And he found something that shook him. For carbon to be produced in stellar cores in the quantities observed, there had to be a very specific energy resonance in the carbon nucleus, a property of the carbon atom that made it dramatically more likely to form than basic physics would predict. Hoyle predicted this resonance before it was experimentally confirmed, and when it was confirmed, he said something remarkable for a scientist who did not believe in God. He said that a superintellect had monkeyed with physics and with chemistry and with biology. He did not become religious, but he acknowledged, in print, that the fine-tuning of the universe for carbon-based life was not something he could explain away as coincidence. Now, what do we do with this? There are 3 serious responses in the scientific and philosophical literature. The first, the constants had to be what they are. There is a deeper theory, not yet discovered, that explains why these values and no others are physically possible. The fine-tuning is real, but it will eventually be explained by mathematics. The second, the constants are what they are because we are here to observe them. In a multiverse, a landscape of many universes, each with different physical constants, we inevitably find ourselves in one that permits our existence. The fine-tuning requires no explanation because all possible values exist somewhere, and we can only ask the question from within the rare universe that allows us to ask it. The third, the constants were chosen. The universe was designed. The fine-tuning is evidence of intention, of a will behind the structure of reality, of something that selected these values because it wanted a universe capable of producing complexity, consciousness, life. None of these answers is satisfying in the way that a mathematical proof is satisfying. None of them closes the question completely. And perhaps that is appropriate. Perhaps some questions are not meant to be closed. Perhaps they are meant to be lived with, carried, returned to across a lifetime. The way the deepest human questions always have been. For as long as human beings have looked at the night sky, they have felt the need to explain it. Not just describe it, explain it. Every civilization that has ever existed has developed some account of why the cosmos is structured the way it is, why human beings exist within it, and what relationship the two bear to each other. The oldest astronomical records we possess, Sumerian clay tablets from 5,000 years ago, Egyptian astronomical ceilings from 3,000 years before the Common Era, the Vedic hymns of ancient India, all reveal a common impulse. The universe is not random. It is not indifferent. It speaks somehow of something beyond itself. The Abrahamic traditions, the three great monotheistic religions that together encompass more than half of all human beings currently alive, share a foundational claim at their core. The universe was created intentionally. The act of creation was an expression of divine will. And the creation, however vast, is in some meaningful sense oriented toward the beings within it capable of consciousness and moral choice. The Quran says that God created the heavens and the earth and everything between them in 6 periods of time, and that the creation was not undertaken in vain. The Torah opens with the deliberate, structured creation of a cosmos in which human beings are given a specific role and responsibility. The Gospel of John opens not with creation but with logos, the word, the rational principle, as the foundation of everything that exists. None of these traditions predicted a universe of 2 trillion galaxies. None of them anticipated the scale of emptiness we have found, but all of them anticipated the question, why is there something rather than nothing? Why is there order rather than chaos? Why in the vastness of whatever exists does awareness arise at all? Modern physics has not answered those questions. It has, if anything, made them sharper, more precise, more impossible to dismiss. Because physics has confirmed something that the ancient traditions could only intuit. The universe is not a random collection of matter. It is a structure of extraordinary mathematical elegance, operating according to laws of breathtaking precision, producing, through a long, patient, costly process, the one thing that seems most improbable of all, a being capable of asking why. The Buddhist tradition, which takes a different approach to creation, nevertheless arrives at a similar insight through a different route. The concept of dependent origination, the idea that all phenomena arise in dependence on conditions, that nothing exists independently or in isolation, maps with surprising precision onto what modern physics tells us about the universe's structure. You could not exist if stars had not died. Stars could not have formed if the fundamental forces were not calibrated as they are. The forces could not have the values they have if the universe had not begun as it did. Everything is connected to everything else across 13.8 billion years of cosmic history. The emptiness that surrounds you, the vast, cold, silent expanse of space, is not separate from you. It is the condition of your existence. The silence is not the absence of the creation's purpose. The silence is the medium through which the purpose is being worked out. Here is something that most people do not know about empty space. It is not empty. In classical physics, the physics of Newton and Maxwell, the physics of everyday human experience, empty space is simply the absence of matter, a void, a nothing in which things move and interact. Quantum field theory tells a completely different story. According to our best understanding of quantum mechanics, empty space is filled with quantum fields, fundamental entities that permeate all of space, and whose excitations we experience as particles: the electromagnetic field, the Higgs field, the fields associated with quarks and leptons, and every particle we have ever detected. These fields are never truly at rest. Even in their lowest energy state, even in what we call the vacuum, they fluctuate. Constantly. Particles and antiparticles flicker into existence and annihilate each other in intervals so brief that they cannot be directly observed, only inferred from their effects. This is not theoretical. The Casimir effect, a measurable force between two uncharged metal plates placed very close together in a vacuum, is direct experimental evidence that the vacuum is not nothing. It has structure, it has energy, it has a kind of restless, invisible activity that fills all of space at all times. And here is why this matters for our question: the early universe, in the first fractions of a second after the Big Bang, was not a featureless, uniform plasma. It was a seething, quantum fluctuating medium in which tiny variations in energy density were constantly arising and disappearing. Most of those fluctuations were too small and too brief to matter, but some were not. Some, through a process called cosmic inflation, a brief period of extraordinarily rapid expansion in the universe's earliest moments, were stretched to cosmic scales. Microscopic quantum variations became macroscopic density fluctuations. Regions of space that were infinitesimally denser than their surroundings became, over hundreds of millions of years, the seeds of everything, the galaxies you see in photographs of the deep sky. The filamentary structure of the cosmic web, the clusters and superclusters of galaxies stretching across hundreds of millions of light years, all of it grew from quantum fluctuations smaller than a proton, expanded to cosmic scale in the first second of the universe's existence. The emptiness of space, which looks like nothing from a human perspective, was the canvas, and the universe painted on it with quantum brushstrokes. The empty planets are not evidence that space is barren. They are evidence that space is still in the middle of a process that began at the smallest possible scale and is working its way, patiently and without haste, toward an outcome we cannot yet fully see. Let us talk about emptiness at three different scales, because the emptiness is not just between planets and stars. It is woven into the fabric of matter itself, the first scale, inside the atom. An atom is mostly empty space. This is something that everyone who has taken a high school physics class has heard. But hearing it and feeling it are different things. The nucleus of a hydrogen atom, a single proton, is approximately 10 to the negative 15 meters across. The electron orbiting that nucleus exists in a probability cloud extending to approximately 10 to the negative 10 meters. The ratio of the nucleus to the atom is roughly 1 to 100,000. If you scaled the nucleus of a hydrogen atom to the size of a marble, about 1 centimeter across, the electron's orbital region would extend to approximately 1 kilometer away. Between the marble and the kilometer, nothing, no matter. No field detectable to human instruments. Just mathematical probability telling you where the electron might be found if you look. The building block of all physical matter is itself almost entirely absence. You are not as solid as you feel. Your body, every atom of it, is overwhelmingly empty. The sensation of solidity comes not from matter filling space, but from the electromagnetic repulsion between electron clouds. The same fundamental force that keeps your hand from passing through a table. You are standing on a vast amount of organized emptiness, held in shape by mathematical forces, and calling it solid, the second scale. Between the stars, the nearest star to our Sun is Proxima Centauri, at a distance of approximately 4.24 light-years. 4 light-years does not sound like much, stated baldly. But light travels at approximately 300,000 kilometers per second. In 1 year, it crosses approximately 9.5 trillion kilometers. The distance to Proxima Centauri is approximately 40 trillion kilometers. If you drove a car at highway speed, 100 kilometers per hour, to Proxima Centauri, the journey would take approximately 43 million years. This is our nearest neighbor. The next nearest star after that is even farther. Between our solar system and Proxima Centauri, a handful of rogue planets, some dust, some hydrogen gas, and an almost incomprehensible amount of cold, dark nothing. The third scale. Between the galaxies, our nearest large galactic neighbor is the Andromeda Galaxy, at approximately 2.5 million light-years, 2.5 million years of light travel, in empty space, just to reach the next significant collection of stars, between the Milky Way and Andromeda. A few satellite galaxies, some gas, some dark matter we cannot directly detect, and an expanse of space so large that if you compress the observable universe into a room, the Milky Way and Andromeda would be two barely visible specks a hand's width apart. At every scale, inside matter, between stars, between galaxies. The universe is overwhelmingly composed of nothing. We live in a universe of emptiness, occasionally interrupted by brief structures of matter. And somehow, in one of those structures, on one level of one layer of one interruption in the emptiness, matter organized itself into something that could look at all of this and ask why. We have followed the physics as far as it takes us. We know the universe is almost entirely empty. We know the laws that produce life also require vast amounts of time and space to operate, making the universe's emptiness a structural feature rather than a design flaw. We know the fundamental constants of nature are calibrated with extraordinary precision to permit the existence of complexity. We know we exist at an early point in cosmic history, with the universe's greatest era of potential complexity still trillions of years ahead. And we know that physics cannot tell us why these laws and not others. Cannot tell us why there is something rather than nothing. Cannot tell us whether the universe was intended or simply is. Those questions fall outside the domain of experiment. They fall into the domain of meaning. And that is where every human tradition, scientific, religious, philosophical, has always been reaching, even when it spoke in different vocabularies. The theologian does not contradict the physicist when she says that the universe was created with intention. She is speaking about something the physicist's instruments cannot measure, the why behind the what. The physicist does not refute the theologian when he demonstrates that the universe's emptiness is a necessary consequence of the laws that produce life. He is explaining the mechanism through which whatever intention exists is expressed. They are not in conflict. They are looking at the same thing from different angles. The emptiness is real. The precision is real. The improbability of your existence is real. The fact that, after 13.8 billion years, matter arranged itself into something capable of contemplating its own origins. That is real. What that means, whether it points toward design or toward fortunate accident or toward something no existing framework has yet named, that question is yours. It has always been yours. Let us consider seriously what it means if the astrophysicists are right. If the universe's biological history is in its early chapters, if the vast majority of intelligence that will ever exist in this universe has not yet existed, if that is true, and the physics makes it plausible, then we are pioneers in a sense that makes all human exploration seem modest by comparison. We are not merely the first humans. We are not merely the first technological civilization. We may be among the first conscious entities in the history of an entire universe. Everything that has ever been thought, every question ever asked, every piece of music ever composed, every mathematical theorem ever proved, every act of love or courage or sacrifice or creativity in the entire recorded history of human civilization, all of it took place in the first fraction of a percent of the universe's biological story. We are the earliest chapters of a book that will be written across trillions of years. That is either the most humbling thing in the history of ideas, or the most extraordinary, or both simultaneously. What does it mean to be the first? In human history, being first often means being alone. It means navigating without a map. It means making mistakes that later arrivals will learn from. It means asking questions that will not be answered in your lifetime, perhaps not for millions of years after your lifetime. But being first also means something else. It means the questions you ask now, the paths of understanding you open, the knowledge you build and leave behind, may echo forward in ways you cannot imagine, may matter to minds so far in the future that the time separating you from them makes the entire history of human civilization look like an afternoon. The empty planets are not God's abandoned projects. They are the universe's future. Worlds that are waiting, not for human colonization perhaps, but for the next phase of a process that has barely begun. We are not looking at an empty universe. We are looking at an early one. Every atom in your body has a history, not a metaphorical history, a literal, chemical, documentable history that stretches across billions of years and encompasses events of extraordinary violence and beauty. The hydrogen in your body, in the water in your cells, in the organic molecules of your DNA, is primordial. It was formed in the first minutes after the Big Bang, when the universe was hot enough and dense enough for protons and neutrons to fuse. The hydrogen you are made of is almost as old as the universe itself. The carbon, the backbone of every biological molecule in your body, was forged inside a star that died before the Earth existed. Inside a stellar core burning at temperatures of 100 million degrees. Helium nuclei fused into carbon through a process that takes millions of years. The oxygen you breathe. The oxygen dissolved in your blood. The oxygen bonded to hydrogen in the water that makes up most of your body. Forged in stellar cores. Scattered by supernovae. Drifting through space for billions of years before being gathered into the gas cloud that collapsed to form our solar system. The iron in your blood. The iron that gives hemoglobin its ability to carry oxygen, without which your brain would fail within minutes, was created in the final moments of a massive star's life, forged in the last stage of stellar nucleosynthesis before the star exhausted its fuel and exploded. You are assembled from the wreckage of dead suns, not as poetry, as chemistry. Every element heavier than hydrogen and helium in your body required a star to live, to burn, and to die. And then it required the material from that dead star to drift through space, to be gathered by gravity, to participate in the formation of a new solar system, to become part of a planet, to become part of an ocean, to become part of chemistry that grew slowly more complex across 4 billion years of geological and biological time. The atoms in your body have been part of dinosaurs, of ancient oceans, of mountain ranges that rose and eroded before the first fish crawled onto land, of air breathed by creatures that have no living descendants, of ecosystems that have vanished without a trace, except in the composition of rocks. For almost the entire history of those atoms, they were matter, they were hydrogen, they were stellar plasma, they were interstellar gas, they were rock, they were ocean, they were biology of various kinds. And then, for a brief period, a cosmic eye blink, they became you, aware, curious, capable of reconstructing the history of the atoms they are made of, capable of understanding, at least partially, the process that produced them, capable of feeling the strangeness and the beauty of their own existence. That is not a small thing by any measure available to us. Scientific, philosophical, spiritual, that is an extraordinary thing. And the empty planets, the silent galaxies, the vast cold dark between the stars. All of it was the preparation for this. The long cooking time before the product could emerge. The patient architecture of a universe learning, through billions of years of trial, how to produce something that could look back at it and understand. We began with a question about God and empty planets. We have traveled through astrophysics and quantum mechanics, and the fine-tuning problem, and the Fermi paradox, and the deep history of the atoms in your body. And we have arrived at the edge of what physics and philosophy can tell us. The universe is almost entirely empty. This is not a failure of creation. It is a feature of the process that produces complexity. The emptiness is the working condition, the substrate, the patient medium through which the universe pursues whatever it is pursuing. The laws of physics are calibrated with extraordinary precision to permit the existence of atoms, stars, planets, chemistry, biology, and ultimately, minds. Whether that precision reflects intention or fortunate accident is a question that current science cannot answer and may never answer. We exist at a very early point in the universe's biological history. The silence we hear when we listen for other minds may be the silence of earliness rather than the silence of absence. We may not be alone, we may simply be first, and we are assembled from the debris of dead stars, atoms with a 13.8 billion year history, temporarily organized into something capable of asking why any of this exists at all. That question, why, is the only thing in the known universe that has no physical explanation. Everything else, every force, every particle, every structure, every process, can in principle be described by physics, can be measured, modeled, predicted. But the question why is different. It does not arise from physics. It arises in spite of physics, or perhaps through it, or perhaps, and this is the possibility that neither science nor religion has fully come to terms with. The question is the universe's way of doing something that cannot be done any other way, reaching toward itself, trying, through the instrument of a conscious mind, to understand its own nature. If that is what consciousness is, if awareness is the universe, developing the capacity for self-knowledge, then every moment of genuine understanding, every moment of authentic wonder, every moment of standing under a night sky and feeling the particular impossible-to-name feeling of being small and vast simultaneously, is not a private human experience. It is the universe experiencing itself, through you. right now. Drifting between Mars and Jupiter, an asteroid travels in complete silence. It has traveled in silence for 4.5 billion years. It knows nothing. It experiences nothing. It is matter in one of its simplest, oldest, most common forms. Unchanged, unreflecting, patient as the void itself. That asteroid is the universe's default. That is what almost everything in the cosmos looks like. And then there is you, made of the same atoms, born of the same stellar explosions, subject to the same gravitational laws, but through a chain of events so improbable that modeling it mathematically requires assumptions that border on the philosophical. Those atoms became something that could look up, that could wonder, that could ask why. The billions of empty planets are not evidence of a universe that failed. They are evidence of a universe that is patient. That took 13.8 billion years to produce something capable of understanding 13.8 billion years. That built the laboratory before the experiment. That laid the foundation before the structure. That prepared the conditions before the life. The empty planets are not God's mistakes. They are the walls of the greatest laboratory in the history of existence. And you, with your borrowed atoms and your brief awareness and your questions that go all the way down, you are what the laboratory was built to produce. The universe didn't create billions of empty planets in spite of you. It created them so that you would be possible. And it created you so that, for the first time in 13.8 billion years of mostly silent, mostly empty, mostly patient becoming, something would finally look at all of it and understand that is what is happening right now, in you.